DC Electricity Part 2, Circuits with Resistance. Section C, Resistance, Sensing and Control. This is the device used to control the voltage in Part B of this series. It's a variable resistor. It has two fixed contacts and one that can slide up and down between them. It uses the GCSE idea that the resistance of a wire is proportional to its length as long as the temperature stays constant. This central contact means we make a circuit with two resistors in series, and it divides up the voltage or potential difference, so it's called a potential-divider circuit. For conductors in series, the voltage across the resistor is proportional to that resistance. This overlay shows the circuit with the layout simplified a bit. Total resistance in this circuit is equal to the sum of the two resistors because they're in series, and we can work out the current by using voltage in divided by total resistance, so V in over R1 plus R2. You can use the same equation to calculate the output voltage, that's current times the second resistance. You can substitute the expression for current into the equation for V out, and so you get V out is equal to V in times R2 all over R1 plus R2. For a simple circuit, V in and R1 are fixed, so V out is proportional to R2, particularly if R1 is quite a lot bigger than R2, in which it is in practical circuits. Example 1 of circuits that use resistance is the thermistor, or temperature-dependent resistor. Thermistors are available in loads of packages. This one is a tiny glass bead which has leads soldered on and electrically insulating sleeves to protect the bare wires. You can also get really heavy-duty armour-plated devices that go into very hostile environments, so extreme temperatures and chemical nastiness. The relationship between resistance and temperature can be measured using this setup. We've got an Aldi meat thermometer here because that's the one in my house with the right range and the best precision. It's dunked into a beaker of hot water. This is the circuit diagram for that, and this is the results table that experiment produced. If you plot that on a graph, you can see it's an example of an exponential curve. So the gradient at any temperature T is a function of the temperature. This kind of mathematical model gets covered in detail at A2. But handily, when you put a thermistor into a potential divider circuit, its output linearises nicely over a quite limited range. This one varies by about 4% per degree Celsius, which is a big change, and it makes it very easy to design circuits that use thermistors. Here is an example of the circuit using a fixed resistor in series with the thermistor. This is the equation that describes the behaviour of the circuit. This is the results of that experiment. So I'm measuring two voltages here, the thermistor voltage, the voltage across the fixed resistor, and the sum of the two voltages just to check that my battery isn't fading. This is what V out across the thermistor looks like. And you see over a big chunk of the range of hot water from a kettle, I'm getting a nice linear looking output. Exam question. If the temperature of the thermistor is increased, will the output voltage of the circuit shown in this video go up or down? Part B. If the supply voltage is 2.80 volts and V out must be 1.80 volts at 50 degrees Celsius, when the resistance of the thermistor is 1.75 kiloohms, what value of fixed resistor must be used? Start with part A. So back to my circuit. We're measuring V out here across the thermistor. And for conductors in series, the voltage across the resistor is proportional to that resistance. The thermistor resistance decreases with increasing temperature. More on that in a later video. So it gets a smaller proportion of the supply voltage across it. V out is measured across the thermistor in this circuit, so as the temperature increases, V out decreases. Part B, we're given a load of data, the supply voltage 2.80 volts, an output voltage that we require 1.80 volts, and a thermistor resistance of 1.75 kiloohms. We're also given a temperature in the question, but that's actually a red herring. You don't need it here, although they might ask you to use it later on in a question. They usually never give you anything in an A-level paper that you're not going to use. We can work out the current is V out over the thermistor, so it's 1.80 volts over 1.75 times 10 to the 3 comes out to 1.02 milliamps. We know that the voltage across the fixed resistor is the supply voltage take away the output voltage. So it's 2.80 volts, take away 1.80, we get exactly 1.00 volts as our voltage drop across the fixed resistor. The fixed resistance can be calculated using V over I. So 1.00 over 1.02 times 10 to the minus 3, we get 9.72 ohms. So about 1 kilo ohm would be the preferred value that's used. Right. Example 2 is the light-dependent resistor, LDR for short. This is a typical light-dependent resistor. Again, many packages are available. They can often be quite smaller than this. The one in your phone is tiny. This one has a decreasing resistance as the light level goes up, which is normal, but you can get ones that work the other way around. They get used in devices like this security lamp. Its function there is to prevent the lamp coming on in daylight, and they also get used for exposure meters in cameras and your phone. This is the underside of the security lamp, and you can see on the left there's a user adjustable dial for at what level of darkness the lamp comes on. The sensor will lurk in the housing along with the PIR at the bottom of the lamp. The circuit that's used in this circuit looks a bit like this. So you've got a power supply in there, you've got the user adjustable resistor at the top, and that's in series with the light dependent resistor at the bottom. The output voltage is measured. In this case, I've drawn it across the light dependent resistor. I used this set of tubes for this experiment. They're made out of black felt, so it soaks up light well, made by sewing felt tubes around a wooden stick, and the purple embroidery you can see as they all have the length of the tube embroidered on them just to avoid confusion. Theory says that light from a point source, which these little light bulb is as nearest diameter point source, spreads out as though it's on the surface of a sphere. So the intensity of light at any distance r from the source is proportional to 1 over the r squared. This is an example of an inverse square law. I first of all had a go at measuring this to see if it's true, and I used my phone for this because all modern smartphones have a light sensor on them as part of the camera, and you can do that if you load your phone with an app that accesses all the sensors. There are lots and lots available, but the one that I'm using here is called SensorBox for Android. I've stuck the lamp at the top of a tube and over the light sensor on the phone. This is an example of the readout, and it's reading in luxes. This is the results from this experiment. So I've got tube length in centimetres, and then the right hand column here is 1 over the length squared in centimetres squared. And if you stick that on a graph, it looks like this. I would call that respectable straight line behaviour. The data on the right of this graph is a bit sparse and also a bit more imprecise than the data closer to 0, but it's respectable. I think I will buy that light intensity varies like 1 over r squared on the basis of this experiment. From semiconductor physics that we cover later in this series, more light gives the light dependent resistor lower resistance, unless it's an unusual positive light coefficient LDR. If this relationship is truly inversely proportional, that means that the intensity of light is proportional to 1 over the resistance. From the phone measurement, we know that shorter tubes give more light intensity, and that there's an inverse square law relationship. Intensity is proportional to 1 over the tube length squared. And this gives a relationship that we can test. Is 1 over the tube length squared proportional to 1 over resistance? And you can simplify that relationship. Is tube length squared proportional to resistance? Okay, this is the kit that I used to test this relationship. So we've got a light source, we've got the tube, the little felt tube, and I've actually stuck a bit of gaffer tape around the light dependent resistor so that it seals well into the bottom of the tube. This is the kit assembled for a measurement. What we're measuring here is the voltage across the power supply, just to make sure it doesn't vary during the experiments. Because of the range of meters that I've got, the light dependent resistor is stuck straight into an ohm meter. These are the results from this experiment. We've got tube length squared, 2 resistance values, and a mean resistance value. Most of my results seem to sit on a straight line. You could probably draw an elegant upward curving line through this lot as well, so I think that this isn't the strongest relationship in the known universe. But on the other hand, the longest tube was also the wobbliest. Felt is not known to be a stiff material, so I think that was the least precise measurement for reasons of wobbly felt. So I'm going to buy this as a relationship and say resistance is proportional to the length of my tube squared. Here is the circuit for an exam question. We've got a 470 ohm resistor in series with an LDR, a 5 volt power supply, and we're measuring V out across the LDR. Exam question. The resistance of the LDR is 500 ohms in full sunlight and 150 kilo ohms in the dark. What is V out in these circumstances? It's a good idea, if you get a circuit diagram, write the data in on the circuit diagram. You own an exam paper, write on that diagram if you want to. So in darkness, the total resistance, our dark total, is the 470 ohms from the fixed resistor and 150 times 10 to the 3 ohms from the LDR, 150,470 ohms. Probably leave that number in my calculator and calculate the current under these circumstances as V supply over R dark total is 5 volts over 150,470 ohms. And that gives me a current in the dark of 33.2 microamps. V out is across the LDR, so it's current that we've just worked out times the resistance in the dark. So 33.2 times 10 to the minus 6 amps times 150 times 10 to the 3 ohms gives us an output voltage of 4.98 volts. In sunlight, it's exactly the same process again, so plug and chug but with different numbers. The sunlight total, 470 plus 500, 970 ohms. The current running through this is 5 over 970, 5.15 milliamp. And we get V out is current times the sunlight resistance, 5.15 times 10 to the minus 3 times 500. V out is 2.58 volts. That's the end of this video. Thank you for watching.